today is we're going to look at 2 more ways to find the total number of possible outcomes. That's still our essential question. How do you find the possible number of outcomes? So far we've done it 2 different ways. We did it visually with a tree diagram. And not only could we find the total number, we could actually see the entire sample space. Now, the next way we learned was counting principle. It was our shortcut. So we didn't have to draw that whole tree. So we got the total number, but we couldn't see what they were. Today we're going to look at 2 others, permutations, which ties directly back into counting principle, and combinations. Now the reason we're doing permutations is because it will really help us understand what's going on with combinations. So if everyone's on page 427 in your workbook, and those of you that are listening to this on YouTube, you can always link to your workbook or your book through the website. Use your school email and your school password. Alright, so permutation. A permutation is what we use when we're selecting a group of objects when order is important. So if order matters, then we would choose permutation. Now, another thing it might say when order matters is how many different ways can we arrange the object. So if you see a range or arrangement of objects, that's keying you in on a permutation because the order matters. So if we think about things where order might matter, let's say you're playing baseball. Would your position matter? Would it matter how the coach makes the lineup? Yeah. You would much rather be the one that bats 4th than the one that bats 9th, wouldn't you? That means they have confidence in you being a good hitter. Okay. All right. So when order matters, we're permutation. So let's take a look at this example. It says the members of a club want to choose a president, a vice president, and a treasurer. We have 7 members of the club that are eligible to fill these positions. And how many different ways can the positions be filled? So you read a question like this, and you're trying to find the total possible outcomes, and you're asking yourself, would the order matter? Would I care if I were president versus vice president? Well, yeah, I want to be president, right? Yeah, okay. So the order does matter. Order matters, permutation. All right, consider the number of ways each position can be filled. There are how many different ways that we can fill that position of president? 7, because we have 7 eligible members. Now we've chosen our president. How many ways can we fill that VP position?
6.
6, because we used 1. And how many people are left to choose from for the treasurer? 5. So this looks just like the counting principle, doesn't it? All right, so let's treat this one like counting principle. We've got our different categories. President, VP, treasurer. Okay, and we're sitting there without a calculator, so we're always thinking, what's the quickest, easiest way to multiply here? Well, 6 times 5 is 30. 30 times 7. 3 times 7 is 21 with a 0, right? 210. Okay, so those of you who approach multiplication the way I just did, what's the easiest way to do this? Quickest, fastest, most correct? I will see you in September. Math team meets Thursday mornings, starting September. So if your brain did that, you should come join us. We have competitions, but not too many. It looks good on your resume. It helps you prepare for the math portion of the SAT and the ACT. And you could be on a team that gets trophies. We like to win. Okay? All right. So, since this one can be set up just like counting principle, I want you to go ahead and try number 1, parts A and B. You try number 1, parts A and B. I'm going to be walking the room. No, I'm not. I got feedback. But raise your hand if you have any questions. I'll come to you. many of you are wishing you brought a calculator today? A few of you, okay. All right, 7 times 6 times 5 times, ooh, this one has a new position, secretary, so it would be 4. Okay, so we just did 7 times 6 times 5 was 210, so 4 times 210 is just 840, right? All right, this one's a little different. We're up to 8 members. The previous 3 positions. So it's 8 times 7 times 6, and so my brain's always thinking, ooh, what's the easiest way? So I'm probably going to do 8 times 42, but I don't want to do old-fashioned math. My brain's always thinking, ooh, what's easier than that? Well, I can think of 42 as 40 plus 2, so that's 320 plus 16, which is 336. Your brain did that. I'll see you in September. Awesome. Okay, we do want to use those things we studied, and the thing is we started studying them in elementary school before our brain was completely ready to understand why we'd ever care. Okay? So this, for me, this is why I care. Doing 8 times 42 in my head is not as easy, but 8 times 40 plus 8 times 2 is pretty easy. Right? All right, we're about to introduce something new. It's called factorial. In factorial, and it's so exciting that they let the symbol that represents factorial be the exclamation point. Okay? So in factorial is how we would read this in exclamation point. It's in factorial. Now, it's a pretty simple concept. If I were to say 4 factorial, what I do is I start with a 4, and I multiply it times every positive integer that is less than 4. So it becomes 4 times 3 times 2 times 1. Done. 4 factorial is 4 times 6, or 24.
Yeah.
Okay? So n factorial is n times the number before that, n minus 1, times the number before that, n minus 2, times dot, 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 all the way down to 3 times 2 times 1. That's what factorial means. That number times every positive integer that is less than that number. Now, because you like math, and because you're bright, you're about to not like this. I'll go ahead and tell you. You're not going to understand why I would show you this simple, easy way of doing it, and then go complicate it on you. But this leads us so nicely into combinations, and then you'll understand. So we're kind of having to think backwards a little bit. We just did this problem where we did 7 times 6 times 5, right? And that's how we figured out how many different ways we could fill those 3 positions, president, vice president, and treasurer, given 7 eligible people. Now, is this equivalent to this? 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1?
Yes.
But they just canceled those?
Yeah.
Now, isn't this string, this multiplication strand, isn't that the same as 7 factorial? And isn't this strand the same as 4 factorial? Well, this 4 factorial, could I get it from 7 minus 3?
Yes.
Okay. So, I'm pushing you a little bit here. But this 7 represented our total that we were working with. There were 7 eligible members. This 3 down here represents how many we're choosing. Do y'all see that? And do you see how I could have gone this direction instead of this direction? This is our formula for permutations. And this is really kind of where the counting principle came from. The number of permutations of n objects taken r at a time. In our case, we had 7 people. We were choosing 3. N objects taken r at a time is the permutations of n choose r equals n factorial over n minus r factorial. That makes no sense until you do a couple of them, and then it makes more sense. So our formula, this is what we want to become comfortable with. The permutations of n choose r. This is how many we have total. This is how many we're choosing. Is the total factorial over the total minus what we're choosing factorial. That's how it always works. Okay, so let's see how we can use this in a probability problem. Okay. In this particular problem, there's a school that assigns a 4-digit code to each student, such as 6953. And they're doing that to access their computer system. But in this particular case, they have a restriction where no digit is repeated. What is the probability that you are assigned a code with these digits, 1, 2, 3, 4, in any order? Well, if we think about probability, probability is the number of favorable events over the number of total possible events. So that denominator, total possible events. We could use counting principle. We could use permutations. In this case, let's use permutations just because they're going to be new to us. So let S represent our total sample space. Find NS. Well, guys, NS, this N means the number. So how many items are in our sample space? What is the number in our sample space? So the sample space consists of all permutations of 4 digits taken from the 10 digits 0 to 9. So we have 10, we're choosing 4. This is our N, this is our R. That is a terrible looking N. Let me try again. Nope, still not good. Just know that's an N. Alright, so it's the permutations of 10 choose 4 is 10 factorial over 10 minus 4 factorial. That 10 factorial, this is where you learn how to do it algebraically. Because my denominator is 6 factorial, the way I would write that is 10 times 9 times 8 times 7 times 6 factorial. And then I would leave the denominator as 6 factorial. Because what could I do with those factorials?
Cancel them
They
out.
cancel. Exactly. Bye-bye. So it's 10 times 9 times 8 times 7. Okay. 72 times 7. 504.
That's 54. Another 40.
And times 10 would be 50, 40. Yeah.
So you don't have to go all the way down.
You don't, because you see that this denominator has that 6 factorial in it. So since 6 factorial and 6 factorial are equivalent, they can cancel. Okay, now the second part is a little interesting. And I think I skipped something when I went over this. I did. It's highly important. Let's go back up here for a second. I said this, that n factorial is a product of n times all the positive integers that are less than n. But we have to define 0 factorial. How many different ways can I arrange nothing? One. 1. So 0 factorial is equivalent to 1. All right. So in this problem, now we're going to find the favorable events. So we're trying to figure out how many different orders I can do of 1, 2, 3, and 4. So if this is all I'm dealing with, 1, 2, 3, and 4, it's the permutations of 4, choose 4, which we know, guys, would be 4 times 3 times 2 times 1 from the counting principle, don't we? But this would give us 4 factorial over 4 minus 4, which is 0 factorial. Well, I just went back up and we defined 0 factorial as 1. So it is 4 times 3 times 2 times 1, which is 24. So this probability is 24 over 540. And this simplifies to 1 over 2/10. Those of you that are sitting over the calculator, please double check all of my calculations. Good? Okay. All right. Okay, now, I told you we were going to learn 2. And permutation is a lot like counting principle, except it might look a little more difficult. But it's that cool formula. And that formula is cool because it gives us the number of arrangements of items when order matters. And now we're going to look at combinations. And a combination is a grouping of objects when order doesn't matter. So let's say I'm driving through Fayetteville and I'm hungry for some donuts. And so I pull into the Dunkin' Donuts and I go in and I decide that I can't decide. So I get a dozen donuts. Now, some with sprinkles, some with chocolate, some not chocolate because my kids don't like chocolate as much as I do. And then I leave with my dozen donuts very happy. Doesn't matter the order that they put those donuts in the box. No, because I am leaving with a group, a collection of donuts. So they might have 20 to choose from and I'm taking 12 and the order that they put them in the box doesn't matter. So if I'm trying to figure out how many different combinations of donuts I can get, it would take me a long time, wouldn't it? If it weren't for this formula. Okay, so luckily I know this formula. And if you were my child, when you lived life with me, things like that would happen. We would go and I'd go, okay, you can choose from these 4, but you can only get 2. How many different ways can we do it? Poor children. Alright, so for example, we're going back to the letters, but do you see this time we've included D? Okay, last time we looked at all of these. Here we had A, B, and C. And when order matters, there's a difference between A, B, C and B, A, C. So when I take these letters A, B, and C and order matters or the arrangement matters, there are 6 different ways I can arrange those letters, right? But what if order doesn't matter? If order doesn't matter, is there any difference between A, B, C and C, A, B? No. And when I use that permutation formula, order did matter, so it gave me 6. Well, with a combination, the order doesn't matter. A, B, C is the same as C, A, B. What matters is that our groups look different. So here we've added a 4th letter, and this first group is A, B, C. The next group is different. It's a different group, A, B, D. And this is A, C, D. And this is B, C, D. Here, how many do I have? I ended up with 1, 2, 3, 4 different groups. With my permutation, when order did matter, I only had 3 letters, and how many groups did I end up with? 6. So a combination is going to give me a much smaller amount. Because I can't count ABC and CBA as 2 different ones. So what we do is we divide by an extra R factorial. What that R factorial does in the denominator is it divides out those duplicates. It takes out the ABC and the CBA. They're the same in a combination. They're the same collection of letters. So the formula for combination is, and I'm going to write a little bigger here, the combinations of n choose R is n factorial over R factorial times n minus R factorial. And this R factorial is dividing out those duplicates. That's what this is doing. That r factorial is dividing out the duplicates. So when we have a combination, this is what we have to do. Okay, on the previous page it gives us an example. It says we're going out to eat. And with our main entree, we have a choice of 3 sides. Now, if we looked at that list, I'm pretty sure we could eliminate some of them as not potential. Beets. Who eats beets? Every class I've asked, and so far no one eats beets. Okay, but beets is an option. So here we have 8 side dishes that we can choose from. How many different ways can you choose 3 different side dishes? So, does the order that they put the food on your plate matter? No, it doesn't. This is a combination. So we would say combination of, how many side dishes do I have to choose from? 8. How many am I choosing?
3.
3. So it's a combination of 8, choose 3. So it would be 8 factorial over. Now, here we have the extra 3 factorial. This 3 factorial is dividing out those duplicates. Because beets, potatoes, and carrots is no different than carrots, potatoes, and beets. So it's 3 factorial over 8 minus 3 factorial. Now, when I do this, 8 factorial, I'm going 8 times 7 times 6 times 5 factorial. Because what is 8 minus 3? 5. I'm going to make my life a little easier. And I know that those 5 factorials will cancel. Now 3 factorial is 3 times 2 times 1. What is 3 times 2?
6.
6. So this 6 can cancel with this 6. And how many different combinations are there? 8 times 7.
56.
56. Alright. So there we go. So that's the change with the combination. We have to have that extra r factorial in the denominator to divide out those duplicates that we get because the order doesn't matter. Alright. What I'd like you to do is I want you to look at, on page 431, 1 through 9, except skip number 7 because it's an error analysis. All you're going to do is determine if it's a permutation or a combination. A permutation or a combination. And then we're only going to work 2 of them. So you're just putting P or C out the side, 1 through 6, and then 8 and 9. While you guys are doing that, I'm going to walk the room and write down your book numbers. If your book is still out on your desk, then I can see the number.
Doesn't matter.
If order matters, it's a permutation. If order does not matter, it's a combination. If order matters, it's a permutation. If order does not matter, it's a combination.
You have 15 code frames. Where's that? One through 9, or you want us to do all of them? Oh yeah, I ripped it all out. It's like 4 pages.
Okay, guys, did I ask if any of those that are requesting a calculator, do any of you have your 4 AAA batteries today? If you do, I will get you your calculator.
Oh, she still haven't got a calculator. You should probably get one.
Either buy one or get one from me,
I
but
know,
you're going to need one.
When are we going to need them?
I don't know, but
Well, I can get one. That's not really a problem.
The newest one, the TI-84. Is there the newest TI-84?
So I mean, if I need it like next week, I'll get one. So we're on Amazon.
Oh, yeah. Yeah, that would be easier.
Go probably down second. I think I'm gonna go see. Wait, where are you? 26 tiles. What are you it's ABC. But it's A2Z, so maybe we should Alright, we're done. Here's my so we'll be like right before we end class, can I run my last time? So I don't miss the hours.
That one's probably like.
I would miss the I don't know where my locker is.
oh, that's true. You got it. Why don't you take that home and leave it at home? Then you can use it at the phone.
I just need that'll work.
Okay, let's take a look at this one. We want different orders. I've marked it out, but that's what it says. Different orders. That's automatically telling me it's a permutation.
Yes.
Order or arrangement matters. Okay, how many different ways? Permutation.
Yes.
I care if I come in first or third, or not one of those.
Yes.
Okay. Assigning who plays which base. Permutation. It matters, the order. Okay? Photographs in your yearbook. Now, you may not care where you are, but this word right here, how many different ways can you arrange? Arrangement, order matters. Okay. In that order, order matters. In any order. Combination.
Yeah. First one.
All right. I'm going to pick up my kittens. I have 6 to choose from in this little box, but I get to pick 2 to take home with me. Does the order in which I pick the kittens matter?
No.
Combination. And then this one. Now, we could argue this. When I go to Six Flags, the order in which I go to my roller coasters does matter because the line matters. But at the end of the day, when I post to Instagram my picture of me looking completely worn out and drenched because I got stuck under the waterfall, does the order in which I rode the roller coasters really matter? No, I just got to ride them. So this is actually a combination. I really liked Batman until somebody told me last period lots of people have died.
What? Oh, that's a lie. That's
Okay, because I let my kids ride it without me, and I just go, oh, look at them.
I liked it when they were
All right. So I want you to go back, and now that we've talked about what it is, let's see if you can show me the one line of math that'll look like the one line of math I want to see on your homework. See if you can set it up. So this one's a permutation, so it's the permutations of how many? 10. How many am I choosing?
3.
3. Let's see if you can do the math.
I got it. Easy peasy. Okay. I think that's
I don't want you to forget why it's there. Because believe it or not, tomorrow I'm going to show you how to do all of this on your calculator.
Why are we doing that?
Why are we doing it today? Because we don't want to become stupid, and we don't want the world to be run by the robots. So, we are going to understand what's going on before I show you the shortcut. Did you get yours off eBay?
Mine?
Yeah.
No, my mom's like friend, her son was going to college, so he just sold it to me for like $50, I think. So, yeah, worked hard.
Just wondering, because the yellow ones, they only sell to schools.
Like red?
But yours is orange, isn't it?
Yeah.
It's not really yellow.
It's orange.
Okay. Yeah, because somebody in another class had a yellow one.
Anthony.
I'm like, oh, did you buy that off eBay? Might not be. Yeah.
His sister gave it to him.
It's alright. It's all good. It's back where it belongs.
Did we just do number 2?
Wait, I'm pretty sure I did.
2 and 9. I'm sorry.
Oh, alright.
It was number 9. 2 and 9. happens. You'd be surprised how often it happens.
File.
Several times last year, somebody walked away with one of those. They don't mean to. They just pack it up with everything else.
I think I did.
Okay, because the bell's going to catch us shortly, let's talk about this. Permutation is n factorial over n minus r factorial. So in this case, it's 10 factorial over 10 minus 3 factorial. So if I'm showing my work, 10 times 9 times 7 factorial over 7 factorial, I'm showing these 7 factorials cancel. So 10 times 8 times 9 is 720. You didn't even have to write that step. You got it right there.
Yeah.
Oh, that's 2.
Okay, that was number 2. Okay, now let's take a look at number 9. This is the combinations of 11 choose 4. So it's 11 factorial over 4 factorial times 11 minus 4 factorial. So when I start writing that 11 factorial out, I'm going to stop at 7 factorial because 11 minus 4 is 7. Now, this 4 factorial, I'm going to go ahead and write out. And you'll see in a second why. The 7 factorials cancel. I'm going to go slow, though, right here. I'm always going with the easiest way to do math. 4 times 2 is 8.
Easy.
That's what we want to make it easy, yes. That's our goal. 4 times 2 is 8, so we cancel that. And then we say 3 goes into 9 3 times. 3 times 11 is 33. Throw a 0 at the end. We're at 330.
Alright, I'm ready to see how to do it.
Okay. Homework. Workbook and a few out of the book.
Are they on the calendar?
This is directly off your calendar.
So I can just pick my book up and leave that. Yeah, you like till the end.
Okay.
The thingy. Till the end.